Unit 5 Surface Chemistry. Some of the most important chemicals are produced industrially by means of reactions that occur on the surfaces of solid catalysts. Surface chemistry deals with phenomena that occur at the surface or interfaces. The interface or surface is represented by separating the bulk phases by a hyphen or a slash. For example, the interface between a solid and a gas may be represented by solid gas or solid slash gas. Due to incomplete miscibility, there is no interface between the gases. The bulk phases that we come across in surface chemistry may be pure, compounds, or solutions. The interfaces are normally a few molecules thick, but its area depends on the size of the particles or bulk phases. Many important phenomena noticeable among these being corrosion, electrode processes, heterogeneous catalysis, dissolution and crystallization occur at interfaces. The subject of surface chemistry finds many applications in industry, analytical work and daily life situations. To accomplish surface studies meticulously, it becomes imperative to have really clean surface. Under very high vacuum of order 10 to the power minus 8 to 10 to the power minus 9 Pascal, it is now possible to obtain ultra clean surface of the metals. Solid materials with such clean surfaces need to be stored in vacuum, otherwise these will be covered by molecules of major components of air like dioxygen and dinitrogen. In this unit we will be studying some important features of surface chemistry such as adsorption, catalysis and colloids, including emulsion and gels. Adsorption. There are several examples which reveal that surface of a solid has tendency to attract and retain molecules of the phase with which it comes into contact. These molecules remain only at surface and do not go deeper into bulk. The accumulation of molecular species at the surface rather than in the bulk of a solid or liquid is termed adsorption. The molecular species or substance which concentrates or accumulates at the surface is termed adsorbate, and the material on the surface on which the adsorption takes place is called adsorbent. Adsorption is essentially a surface phenomena. Solids, particularly in finely divided state, have large surface area and therefore charcoal, silica gel, alumina gel, clay, colloids, metals in finely divided state, etc. acts as good adsorbent. Adsorption and reaction. If a gas like O2H2CO, Cl2, NH3 or SO2 is taken in a closed vessel containing powdered charcoal, it is observed that the pressure of the gas in enclosed vessel decreases. The gas molecules concentrate at the surface of the charcoal, that is, gas are adsorbed at the surface. In a solution of an organic dye, say methylene blue, when animal charcoal is added and solution is well shaken, it is observed that the filtrate turns colorless. The molecules of the dye thus accumulate on the surface of charcoal, that is, are adsorbed. Aqueous solution of raw sugar, when passed over beds of animal charcoal, becomes colorless as the coloring substances are adsorbed by charcoal. The air becomes dry in the presence of silica gel because the water molecules get adsorbed on the surface of the gel. It is clear from the above examples that solid surfaces can hold the gas or liquid molecules by virtue of adsorption. The process of removing an adsorbed substance from a surface on which it is adsorbed is called desorption. Distinction between absorption and adsorption. In adsorption, the substance is concentrated only at the surface and does not penetrate through the surface to the bulk of the adsorbent, while in absorption, the substance is uniformly distributed throughout the bulk of the solid. For example, when a chalk stick is dipped in ink, the surface retains the color of the ink due to adsorption of colored molecules, while the solvent of the ink goes deeper into stick due to the absorption. On breaking the chalk stick, it is found to be white from inside. A distinction can be made between absorption and adsorption by taking an example of water vapor. Water vapors are absorbed by anhydrous calcium chloride but absorbed by silica gel. In other words, in adsorption, the concentration of adsorbate increases only at the surface of adsorbent, while in the absorption, the concentration is uniform throughout the bulk of the solid. Both adsorption and absorption can take place simultaneously also. The term sorption is used to describe both the processes. Mechanism of adsorption. Adsorption arises due to the fact that the surface particles of the adsorbent are not in the same environment as the particle inside the bulk. Inside the adsorbent, all the forces acting between the particles are mutually balanced, but on the surface, the particles are not surrounded by atoms or molecules of their kind on all sides, and hence they possess unbalanced or residual attractive forces. These forces of adsorbent are responsible for attracting the adsorbate particles on its surface. The extent of absorption increases with the increase of surface area per unit mass of the adsorbent at a given temperature and pressure. Another important factor featuring adsorption is the heat of adsorption. During adsorption, there is always a decrease in residual forces of the surface, that is, there is decrease in surface energy which appears as heat. Adsorption therefore is invariably an exothermic process. In other words, delta H of adsorption is always negative. When a gas is adsorbed, the freedom of movement of its molecule becomes restricted. This amounts to decrease in entropy of the gas after adsorption, that is, delta S is negative. Adsorption is thus accompanied by a decrease in enthalpy as well as decrease in entropy of the system. For a process to be spontaneous, the thermodynamic requirement is that at constant temperature and pressure, delta G must be negative, that is, there is decrease in Gibbs energy. On the basis of equation delta G equals to delta H minus T delta S, delta G can be negative if delta H has sufficiently high negative value as minus T delta S is positive. Thus, in an adsorption process, which is spontaneously a combination of these two factors, makes delta G negative. As the adsorption proceeds, delta H becomes less and less negative. Ultimately, delta H becomes equal to T delta S and delta G becomes 0. There are mainly two types of adsorption of gases on solids. If accumulation of gas on the surface of a solid occurs on the account of weak van der Waals forces, the adsorption is termed as physical adsorption or physiosorption. When the gas molecules or atoms are held to the solid surface by chemical bonds, the adsorption is termed as chemisorption or chemical adsorption. The chemical bonds may be covalent or ionic in nature. Chemisorption involves a high energy of activation and is therefore often referred to as activated adsorption. Sometimes these two processes occur simultaneously and it is not easy to ascertain the type of adsorption. A physical adsorption at low temperature may pass into chemisorption as the temperature is increased. For example, dihydrogen is first adsorbed on nickel by van der Waals forces. Molecules of hydrogen then dissociate to form hydrogen atoms which are held on the surface by chemisorption. Some of the important characteristics of both types of adsorption are given below. Characteristics of physiosorption: lack of specificity. A given surface of an adsorbent does not show any preference for a particular gas as the van der Waals forces are universal. Second, nature of adsorbate. The amount of gas absorbed by a solid depends on the nature of gas. In general, easily liquefiable gases are readily absorbed as van der Waals forces are stronger near the critical temperatures. Thus, 1 gram of activated charcoal adsorbs more sulfur dioxide than methane, which is still more than 4.5 ml of dihydrogen. Reversible nature. Physical adsorption of a gas by a solid is generally reversible. Thus, solid plus gas is irreversible, gas in solid plus heat. More of gas is adsorbed when pressure is increased as the volume of the gas decreases, and the gas can be removed by decreasing pressure since the adsorption process is exothermic. The physical adsorption occurs readily at low temperature and decreases with increasing temperature. Surface area of adsorbent. The extent of adsorption increases with the increase of surface area of the adsorbent. Thus, finely divided metals and porous substances having large surface areas are good adsorbents. Enthalpy of adsorption. No doubt, physical adsorption is an exothermic process, but its enthalpy of adsorption is quite low. Thus, this is because of the attraction between gas molecules and solid surface is only due to weak van der Waals forces. Characteristics of chemisorption. High specificity. Characteristics of chemisorption. High specificity. Chemisorption is highly specific and it will only occur if there is some possibility of chemical bonding between adsorbent and adsorbate. For example, oxygen is absorbed on metals by virtue of oxide formation and hydrogen is absorbed by transition metals due to hydride formation. Irreversibility. As chemisorption involves compound formation, it is usually irreversible in nature. Chemisorption is also an exothermic process, but the process is very slow at low temperatures on account of high energy of activation. Like most chemical changes, adsorption often increases with rise of temperature. Physisorption of a gas adsorbed at low temperature may change into chemisorption at high temperature. Usually, high surface pressure is favorable for chemisorption. Surface area. Like physical adsorption, chemisorption also increases with increase of surface area of the adsorbent. Enthalpy of adsorption. Enthalpy of chemisorption is high as it involves chemical bond formation. Comparison. Physisorption arises due to van der Waals forces. Chemisorption is because of chemical bond formation. Physisorption is not specific in nature, whereas chemisorption is highly specific in nature. Physisorption is reversible in nature. Chemisorption is irreversible in nature. Physisorption depends on the nature of the gas. More easily liquefiable gases are adsorbed readily. Chemisorption also depends on the nature of gas. Gases which can react with the adsorbent show chemisorption. Enthalpy of adsorption is low in physisorption, and enthalpy of adsorption is high in chemisorption. Low temperature is favorable for adsorption in physisorption, and high temperature is favorable for adsorption in physisorption. No appreciable activation energy is needed in physisorption, whereas high activation energy is sometimes needed. Physisorption depends on the surface area and it increases with an increase of surface area. Chemisorption depends on surface area as well. It increases with an increase of surface area. Physisorption results into multimolecular layers of adsorbent surface under high pressure, whereas chemisorption results in unimolecular layer. Adsorption isotherms. The variation of amount of gas adsorbed by adsorbent with pressure at constant temperature can be expressed by means of a curve termed as adsorption isotherm. Freundlich adsorption isotherm. Freundlich in 1909 gave an empirical relationship between the quantity of gas adsorbed by unit mass of solid adsorbent and pressure at a particular temperature. The relationship can be expressed in the following equation: x by m is equals to k into p to the power 1 by n, where x is the mass of a gas adsorbed on a mass m of the adsorbent at pressure p. K and n are constant which depend on the nature of the adsorbent and the gas at a particular temperature. The relationship is generally represented in the form of a curve where mass of gas adsorbed per gram of adsorbent is plotted against pressure. These curves indicate that at fixed pressure there is a decrease in physical adsorption with increase in temperature. These curves always seem to approach saturation at high pressure. Taking log x by m is equals to log k plus 1 by n log p. The validity of Freundlich isotherm can be verified by plotting log x by m on y-axis and log p on p-axis and x-axis. If it comes to a straight line, then Freundlich isotherm is valid, otherwise not. The slope of the straight line gives the value of 1 by n. The intercept on the y-axis gives the value of log k. Freundlich isotherm explains behavior of adsorption in an approximate manner. The factor 1 by n can have values between 0 and 1. Thus, equation holds a good over a limited range of pressure. Where 1 by n is equals to 0, x by m is equals to constant, the adsorption is independent of pressure. Where 1 by n is equals to 1, x by m is equals to k, that is, adsorption varies directly with pressure. Both the conditions are supported by experimental results. The experimental isotherms always seem to approach saturation at high pressure. This cannot be explained by Freundlich isotherm, thus it fails at high pressure. Adsorption from solution phase. Can absorb solutes from solutions also. When a solution of acetic acid in water is shaken with charcoal, a part of the acid is absorbed by the charcoal and the concentration of acid decreases in the solution. Similarly, litmus solution when shaken with charcoal becomes colorless. The precipitate of MgOH whole twice attains blue color when precipitated in presence of magnesium reagent. The color is due to adsorption of magnesium. The following observations have been made in case of adsorption from solution phase. The extent of adsorption decreases with an increase in temperature. The extent of adsorption increases with an increase of surface area of adsorbent. The extent of adsorption depends on the concentration of the solute in solution. The extent of adsorption depends on the nature of adsorbent and adsorbate. The precise mechanism of adsorption from solution is not known. Freundlich's equation approximately describes the behavior of adsorption from solution with the difference that instead of pressure, concentration of the solution is taken into account. X by m is equal to k c to the power 1 by n. C is equilibrium concentration. On taking log x by m is equals to log k plus 1 by n log c. Plotting log c against log x by m, a straight line is obtained. It shows validity of Freundlich isotherm. This can be tested experimentally by taking solutions of different concentrations of acetic acid. Equal volumes of solutions are added to equal amounts of charcoal in a flask. The final concentration is determined by each flask after adsorption. The difference in initial and final concentration gives the value of x. Using our equation, validity of Freundlich isotherm can be established. Application of adsorption. The phenomena of adsorption finds a number of applications. Important ones are listed here. Production of high vacuum. The remaining traces of air can be adsorbed by charcoal from a vessel evacuated by a vacuum pump to give a very high vacuum. Gas mask. Gas mask, a device which consists of activated charcoal or mixture of adsorbents, is usually used for breathing in coal mines to adsorb poisonous gases. Control of humidity. Silica and alumina gels are used as adsorbent for removing moisture and controlling humidity. Removal of coloring matter from solutions. Animal charcoal removes colors of solutions by adsorbing colored impurities. Heterogeneous catalysis. Adsorption of reactant on the solid surface of the catalyst increases the rate of reaction. There are many gaseous reactions of industrial importance involving solid catalysts. Manufacture of ammonia using iron as a catalyst. Manufacture of H2SO4 by contact process and use of finely divided nickel in the hydrogenation of the oils are excellent example of heterogeneous catalysis. Separation of inert gas due to difference in degree of adsorption by gases. By charcoal, a mixture of noble gases can be separated by adsorption on coconut charcoal at different temperatures. In curing diseases, a number of drugs are used to kill germs by getting adsorbed on them. Froth flotation process. A low-grade sulfide ore in concentration by separating it from silica and other earthy matter by this method using pine oil and frothing agent. Adsorption indicators. Surface of certain precipitates such as silver handles, silver halides have the property of adsorbing some dyes like oizine, fluorescein, etc. and thereby producing a characteristic color at the endpoint. Chromatographic analysis. Chromatographic analysis based on the phenomena of adsorption finds a number of applications in analytical and industrial fields. Catalysis. Potassium chlorate, when heated strongly, decomposes slowly, giving dioxygen. The decomposition occurs in the temperature range of 658 to 873 Kelvin. 2 KClO3 gives 2 KCl plus 3O2. However, then a little manganese dioxide is added. The decomposition takes place at a considerably low temperature range, that is 473 to 633 Kelvin, and also at a much accelerated rate. The added manganese dioxide remain unchanged with respect to mass and composition. In a similar manner, the rates of number of chemical reactions can be altered by mere presence of a foreign substance. The systematic study of effect of various foreign substances on the rates of chemical reactions was made by Berzelius in 1835. He suggested that the term catalyst for substances which accelerate the rate of chemical reaction and themselves remain chemically and quantitatively unchanged after the reaction are known as catalysts, and the phenomena is known as catalysis. You already studied about catalyst and its functioning in section 4.5. Promoters and poisons. Promoters are substances that enhance the activity of a catalyst, while poisons decrease the activity of a catalyst. For example, in Haber's process of manufacture of ammonia, molybdenum acts as promoter of iron, which is used for catalysis. Catalysis can be broadly divided into two groups. Homogeneous catalysis. When the reactants, products and catalysts are in same phase, the process is said to be homogeneous catalysis. The following are some examples of homogeneous catalysis: oxidation of sulfur dioxide into sulfur trioxide with dioxygen in the presence of oxides of nitrogen as the catalyst in the lead chamber process. The reactant sulfur dioxide and oxygen and the catalyst nitric oxide are all in same phase. Hydrolysis in methyl acetate is catalyzed by hydrogen plus ions furnished by hydrochloric acid. Both the reactant and catalyst are in same phase. Hydrolysis of sugar in catalyst by hydrogen plus ions furnished by sulfuric acid. Both the reactant and catalysis are in the same phase. Heterogeneous catalysis. A catalytic process in which reactant and the catalyst are in different phases is known as heterogeneous catalysis. Some of the examples of heterogeneous catalysis are oxidation of sulfur dioxide into sulfur trioxide in presence of platinum. The reactant is in gaseous state while the catalyst is in solid state. Combination between dinitrogen and dihydrogen to form ammonia in the presence of finely divided iron in Haber's process. The reactants are in gaseous state while catalyst is in solid state. Oxidation of ammonia into nitric acid in the presence of platinum gas in Oswald process. The reactant are in gaseous state while catalyst is in solid state. Hydrogenation of vegetable oils in the presence of finely divided nickel as catalyst. One of the reactant is in liquid state, other is in gaseous state while the catalyst is in solid state. Adsorption theory of heterogeneous catalysis. This theory explains the mechanism of heterogeneous catalysis. The old theory known as adsorption theory of catalysis was that the reactants in solid state or in solutions are adsorbed on the surface of solid catalyst. The increase in concentration of the reactants on the surface increases the rate of reaction. Adsorption being an exothermic process, the heat of adsorption is utilized in enhancing the rate of reaction. The catalytic action can be explained in terms of intermediate compound formation, the theory of which you have already studied in section 4.5.1. The modern adsorption theory is a combination of intermediate compound formation theory and old adsorption theory. The catalytic activity is localized on the surface of the catalyst. The mechanism involves 5 steps: diffusion of reactants to the surface of the catalyst, adsorption of reactant molecules on the surface of catalyst, occurrence of a chemical reaction on the catalyst surface through formation of an intermediate, desorption of reaction products from the catalyst surface and thereby making the surface available again for more reaction to occur, diffusion of reaction products away from catalyst surface. The surface of the catalyst, unlike the inner part of the bulk, has free valencies which provide the seat for chemical forces of attraction. When a gas comes into contact with such a surface, its molecules are held up due to loose chemical combination. If different molecules are adsorbed side by side, they may react with each other, resulting in the formation of new molecules. Thus, formed molecules may evaporate, leaving the surface for the fresh reactant molecules. This theory explains why the catalysts remain unchanged in mass and chemical composition at the end of reaction and is effective even in small quantities. However, it does not explain the action of catalytic promoters and catalytic poisons. Important features of solid catalyst activity. The activity of catalyst depends upon the strength of chemisorption to a large extent. The reactant must be adsorbed reasonably strongly to the catalyst to become active. However, they must not get adsorbed so strongly that they are immobilized and other reactants are left with no space on the catalyst surface for adsorption. It has been found for hydrogenation reaction. The catalytic activity increases from group 5 to group 11 metals, with maximum activity being shown by group 7 to 9 of the periodic table. Selectivity. The selectivity of a catalyst is the ability to direct a reaction to yield a particular product selectively. When under the same reaction conditions, many products are possible. Selectively of different catalysts for same reactants is different. For example, starting with H2 and CO and using different catalysts, we get different products. Thus, it can be inferred that the action of a catalyst is highly selective in nature. As a result, substance which acts as catalyst in one reaction may fail to catalyze another reaction. Shape selective catalysis by zeolites. The catalytic reaction depends upon the pore structure of the catalyst and size of the reactant and product molecules is called shape selective catalysis. Zeolites are good shape selective catalysts because of their honeycomb like structure. They are microporous aluminosilicates with three-dimensional network of silicates in which some silicon atoms are replaced by aluminium atoms, giving ALOSI framework. The reactions taking place in zeolites depend upon the size and shape of reactant and the product molecules as well as upon the pores and cavities of the zeolites. They are found in nature as well as synthesized for catalytic selectivity. Zeolites are being very widely used as catalysts in petrochemical industries for cracking of hydrocarbons and isomerization. An important zeolite catalyst used in petroleum industry is ZSM5. It converts alcohol directly into gasoline by dehydrating them into a mixture of hydrocarbons. Enzyme catalysis. Enzymes are complex nitrogenous organic compounds which are produced by living plants and animals. They are actually protein molecules of high molecular mass and form colloidal solution in water. They are very effective catalysts. Catalyze numerous reactions, especially those connected with natural processes. Numerous reactions that occur in body of animals and plants to maintain the life of process are catalyzed by enzymes. The enzymes thus are termed as biochemical catalysts and the phenomena is known as biochemical catalysis. Many enzymes have been obtained in pure crystalline state from living cells. However, the first enzyme was synthesized in the laboratory in 1969. The following of example enzyme catalyst reactions. Inversion of cane sugar. The invertase enzyme converts cane sugar into glucose and fructose. Conversion of glucose into alcohol. The zymase enzyme converts glucose into ethyl alcohol and carbon dioxide. Conversion of starch into maltose. The diastase enzyme converts starch into maltose. Conversion of maltose into glucose. The maltase enzyme converts maltose into glucose. Decomposition of urea into ammonia and carbon dioxide. The enzyme urease catalyzes this decomposition. In stomach, the pepsin enzyme converts proteins into peptides, while in intestine, the pancreatic trypsin converts proteins into amino acid by hydrolysis. Conversion of milk into curd. It is an enzymatic reaction brought about by lactobacilli enzyme present in curd. Characteristics of enzyme catalysis. Enzyme catalysis is unique in its efficiency and a high degree of specificity. The following characteristics are exhibited by enzyme catalysts. Most highly efficient. One molecule of an enzyme may transform 1 million molecules of the reactant per minute. Highly specific nature, each enzyme is specific for a given reaction, that is, one catalyst cannot catalyze more than one reaction. For example, the enzyme urease catalyzes the hydrolysis of urea only, it does not catalyze hydrolysis of any other amide. Highly active under optimum temperature. The rate of an enzyme reaction becomes maximum at a definite temperature called the optimum temperature. On either side of the optimum temperature, the enzyme activity decreases. The optimum temperature range for enzymatic activity is 298 to 310 Kelvin. Human body temperature being 310 Kelvin is suited for enzyme catalyzed reactions. Highly active under optimum pH. The rate of enzyme catalyzed reaction is maximum at a particular pH called optimum pH, which is between pH values 5 to 7. Increasing activity in presence of activators and coenzymes. The enzymatic activity is increased in the presence of certain substances known as coenzymes. It has been observed that a small non-protein vitamin is present along with an enzyme, the catalytic activity is enhanced considerably. Activators are generally metal ions such as Na positive, Mn2 positive, cobalt 2 positive, copper 2 positive, etc. These metal ions, when weakly bonded to enzyme molecules, increases their catalytic activity. Amylase is presence of sodium chloride are catalytically very active. Influence of inhibitors and poisons. Like ordinary catalysts, enzymes are also inhibited or poisoned by the presence of certain substances. The inhibitors or poisons interact with the active functional groups on the enzyme surface and often reduce or completely destroy the catalytic activity of the enzymes. The use of many drugs is related to their action and enzyme inhibitor in the body. Mechanism of enzyme catalysts. There are a number of cavities present on the surface of colloidal particles of enzymes. These activities are of characteristic shapes and possesses active groups such as NH2, COOH, SH, OH, etc. These are actually the active centers of the surface of enzyme particles. The molecules of reactant, which have complementary shape, fit into these cavities just like a key fit into its lock. On account of presence of active groups, an activated complex is formed which then decomposes to yield the products. Thus, the enzyme catalyzed reaction may be considered to proceed in two steps: binding of enzyme to substrate to form an activated complex, decomposition of activated complex to form product. Catalyst in industries. Some of the important technical catalytic processes are listed below. Colloids. We have learned in Unit 2 that solutions are homogeneous systems. We also know that sand and water, when stirred with a given substance, which slowly settles down with time. Between the two extremes of suspensions and solutions, we come across a large group of systems called colloidal dispersion or simply colloids. A colloid is a heterogeneous system in which one substance is dispersed as very fine particles in another substance called dispersion medium. The essential difference between a solution and a colloid is that the particle size. While in solution, the constituent particles are ions or small molecules, in a colloid, the dispersed phase may consist of particles of a single macromolecule or an aggregate of many atoms, ions or molecules. Colloidal particles are larger than simple molecules but small enough to remain suspended. The range of diameters is between 1 to 1000 mm. Nm is nanometer, that is 10 to the power minus 9 to 10 to the power minus 6 meter. Colloidal particles have an enormous surface area per unit mass as a result of their small size. Consider a cube with 1 cm side. It has a total surface area of 6 cm square. If it were divided equally into 10 to the power 12 cubes, the cubes would have the size of larger colloidal particles and have a total surface area of 60,000 cm square. The enormous surface area leads to some special properties of colloids to be discussed later. Classification of colloids. Classification are based on following criteria. physical state of dispersed phase and dispersion medium, nature of interaction between dispersed phase and dispersion medium, and types of particle of dispersed phase. Classification based on state of dispersed and dispersion medium. Depending upon whether dispersed phase and dispersion medium are solid, liquid, or gas, 8 types of colloidal system are possible. A gas mixed with another gas forms a homogeneous mixture, hence is not a colloidal system. Examples of various types of colloids are listed with their typical names. Many familiar commercial products and natural objects are colloids. For example, whipped cream is a foam, which is a gas dispersed in a liquid. Firefighting foams used at emergency plane landings are also colloidal systems. Most biological are aqueous sols, solid dispersed in water. Within a typical cell, protein and nucleic acid are colloidal sized particles dispersed in an aqueous solution of ions and small molecules. Out of the various types of colloids, the most common are sols, solids in liquids, gels, liquids in solids, and emulsions, liquids in liquids. However, in this unit, we shall take up discussion of sols and emulsions only. Further, it may be mentioned that if the dispersion medium is water, the sol is called aquasol or hydrosol. If the dispersion medium is alcohol, it is called alkosol, and so on. Classification based on nature of interaction between dispersed phase and dispersed medium. Depending upon the nature of interaction between dispersed phase and the dispersion medium, the colloidal sols are divided into two categories, lyophilic and lyophobic. If water is dispersion medium, the terms are used as hydrophilic and hydrophobic. Lyophilic colloids, the word lyophilic means liquid loving colloidal sols, directly formed by mixing substances like gum, gelatin, starch, rubber, etc. with a superlative liquid are called lyophilic sols. An important characteristic of these sols is that if the dispersion medium is separated from the dispersed phase, the sol can be reconstituted by simply remixing the dispersion medium. That is why these sols are also called reversible sols. Furthermore, these sols are quite stable and cannot be easily coagulated. Lyophobic sols. Lyophobic colloids. The word lyophobic means liquid hating. Substances like metals, their sulfides, when simply mixed with the dispersion medium, do not form colloidal sol. Their colloidal sol can be prepared only by special methods. Such sols are called lyophobic sols. These sols are readily precipitated on addition of small amount of electrolytes by heating or by shaking, and hence are not stable. They cannot give back the colloidal sol by simple addition of the dispersion medium, hence these sols are also called irreversible sols. Lyophobic sols need stabilizing agents for their preservation. Classification based on type of particles of the dispersed phase, multimolecular and macromolecular, and associated colloids. Depending upon the type of particles of the dispersed phase, colloids are classified as multimolecular, macromolecular, and associated colloids. Multimolecular colloids, on dissolution, a large number of atoms or small particles of substance together aggregate to form species having size of colloidal range 1 to 1000 nanometer. The species thus formed are called multimolecular colloids. For example, a gold sol may contain particles of various sizes having many atoms. Sulfur sol consists of many particles containing 1000 or more S8 sulfur molecules. Macromolecular colloids. Macromolecules in suitable solvents form solutions which size of macromolecules may be in the colloidal range. Such systems are called macromolecular colloids. These colloids are quite stable and resemble true solutions in many respects. Example of naturally occurring macromolecule are starch, cellulose, protein, and enzymes. And those man-made macromolecules are polythene, nylon, polystyrene, synthetic rubber, etc. Associated colloids. There are substances which at low concentration behave at normal solar electrolytes, but at higher concentration exhibit colloidal behavior due to formation of aggregates. The aggregated particles thus formed are called micelles. These are also known as associated colloids. The formation of micelles takes place only above a particular temperature called Kraft temperature and above a particular concentration called critical micelle concentration. On dilution, these colloids revert back to individual ions. Surface active agents such as soaps and synthetic detergents belong to this class. For soaps, the CMC is 10 to the power minus 4 to 10 to the power minus 3 mole liter inverse. These colloids have both lyophilic and lyophilic part. Micelles may contain as many as 100 molecules or more. Mechanism of micelles formation. Let us take an example of soap solution. Soap is medium of sodium or potassium salt of higher fatty acid and may be represented as RCOO-Na, which is a major component in many soaps. When dissolved in water, it dissociates into RCOO and Na positive ions. The RCOO negative ions, however, consist of two parts: a long hydrocarbon chain R, which is hydrophobic, and a polar group COO negative, which is hydrophilic. The RCOO ions are therefore represented on the surface with their COO negative in water and the hydrocarbon chains staying away from it and remain at the surface, but at critical micelle concentration, the anions are pulled into bulk of the solution and aggregate to form spherical shape with their hydrocarbon chains pointing towards the center of the sphere and COO negative part remaining outward on the surface of sphere. An aggregate thus formed is known as ionic micelle. These micelles may contain as many as 100 such ions. Similarly, in case of detergents, sodium lauryl sulfate, the polar group is SO4 negative along with the long hydrocarbon chain. Hence, the mechanism of micelle formation is same as that of soaps. Cleansing action of soaps. It has been mentioned earlier that micelle consists of hydrophobic carbon like central core. The cleansing action of soap is due to the fact soap molecules form micelle around the oil droplet in such a way that hydrophobic part of the stearate ions is in the oil droplet and the hydrophilic part projects out of the grease droplet like the bristles. Since the polar groups can interact with water, the oil droplet surrounded by stearate ions is now pulled in water and removed from dirty surface. Thus, soaps help in emulsification and washing away of oils and fats. The negatively charged sheet around the globules prevent them from coming together and forming aggregates. Preparation of colloids. A few important methods for preparation of colloids are as chemical method. Colloidal dissolution can be prepared by chemical reaction leading to formation of molecules by double decomposition, oxidation, reduction or hydrolysis. These molecules then aggregate leading to formation of sols. Electrical disintegration or Briggs arc method. This process involves dispersion as well as condensation. Colloidal sols of metals such as gold, silver, platinum can be prepared by this method. In this method, electric arc is struck between the electrodes of the metal immersed in dispersion medium. The intense heat produced vaporizes the metal, which then condenses to form particles of colloidal size. Peptidation. Peptidation may be defined as process of converting a precipitate into colloidal sol by shaking it with dispersion medium in the presence of small amount of electrolyte. Electrolyte used for this purpose is called peptiding agent. This method is applied generally to convert a freshly prepared precipitate into a colloidal sol. During peptidation, the precipitate absorbs one of the ions of the electrolyte on its surface. This causes the development of positive or negative charge on precipitates, which ultimately break up into smaller particles of the size of a colloid. You will learn about the phenomena of development of charge on solid particles and their dispersion under the heading charge on colloidal particles. Purification of colloidal solutions. Colloidal solutions when prepared generally contain excessive amount of electrolytes and other soluble impurities, while the presence of traces of electrolyte is essential for stability of colloidal solution. Larger quantities coagulate it. It is therefore necessary to reduce the concentration of these soluble impurities to a requisite minimum. The process used for reducing the amount of impurities to a requisite minimum is known as purification of colloidal solution. It is done by following method. Dialysis. It is the process of removing of dissolved substance from a colloidal solution by means of diffusion through a suitable membrane. Since particles in a true solution can pass through animal membrane of parchment paper or cellophane sheet but not colloidal particles, the membrane can be used for dialysis. The apparatus used for this purpose is called dialyzer. A bag of suitable membrane containing the colloidal solution is suspended in a vessel through which fresh water is continuously flowing. The molecules and ion diffuse through membrane into the outer water and pure colloidal solution is left behind. Electrodialysis. Ordinarily, the process of dialysis is quite slow. It may be made faster by applying an electric field if the dissolved substance in the impure colloidal particle solution is only an electrolyte. The process is named as electrodialysis. The colloidal solution is placed in a bag of suitable membrane while pure water is taken outside. Electrodes are fitted in the compartment. The ions present in the colloidal solution migrate out to oppositely charged electrodes. Ultrafiltration is the process of separating the particles from the solvent and soluble solutes present in the filters, which are permeable to all substances except the colloidal particles. Colloidal particles can pass through ordinary filter paper because the pores are too large. However, the pores of filtering paper can be reduced in size by impregnating with colloidal solution to stop the flow of colloidal particles. The usual colloidal is a 4% solution of nitrocellulose in a mixture of alcohol and ether. An ultrafilter may be prepared by soaking the paper in a colloidal solution, hardening by formaldehyde, and then finally drying it. Thus, by using ultrafilter paper, the colloidal particles are separated from rest of the materials. Ultrafiltration is a slow process. To speed up the process, pressure or suction is applied. The colloidal particles are left on ultrafilter paper and then stirred with fresh dispersion medium to get a pure colloidal solution. Properties of colloidal solutions. Various properties exhibited by colloidal solutions are described. Colligative properties. Colloidal particles being bigger aggregates, the number of particles in a colloidal solution is comparatively small as compared to a true solution. Hence, the values of colligative properties are of small order as compared to values shown by true solutions at same concentrations. Tyndall effect. If a homogeneous place in a dark and observed in the direction of light, it appears clear that from a direction at right angles to the direction of light beam, it appears perfectly dark. Colloidal solutions viewed in the same way may also appear reasonably clear or translucent by the transmitted light, but they show a mild to strong oppositions when viewed at right angles to the passage of light. That is, the path of beam is illuminated by a bluish light. This effect was first observed by Faraday and later studied in detail by Tyndall and is termed as Tyndall effect. The bright cone of the light is called Tyndall cone. The Tyndall effect is due to the fact that colloidal particles scatter light in all directions in space. The scattering of light illuminates the path of beam in the colloidal dispersion. Tyndall effect can be observed during the projection of picture in the cinema hall due to scattering of light by dust and smoke particles present there. Tyndall effect is observed only when the following two conditions are satisfied. First, the diameter of dispersed particle is not much smaller than the wavelength of the light used, and the refractive indices of the dispersed phase and the dispersant medium differ greatly in magnitude. Tyndall effect is used to distinguish between a colloidal and true solution. Zsigmondy in 1903 used Tyndall effect to set up apparatus known as an ultramicroscope. An intense beam of light is focused on the colloidal solution contained in a glass vessel. The focus of the light is then observed with a microscope at right angles to the beam. Individual colloidal particles appear as bright stars against the dark background. Ultramicroscope does not render actual colloid particles visible but only observe the light scattered by them. Thus, ultramicroscope does not provide any information about the size and shape of colloidal particles. Color. The color of colloidal solution depends on the wavelength of light scattered by the dispersed particles. The wavelength of light further depends on the size and nature of particles. The color of colloidal solution also changes with the manner in which the observer receives the light. For example, a mixture of milk and water appears blue when viewed by reflected light and red when viewed by transmitted light. Finest gold soul in red in color, and the size of particles increases, it appears purple, then blue, and finally golden. Brownian movement. When colloidal solutions are viewed under a powerful multi-microscope, the colloidal particles appear to be in a state of continuous zigzag motion all over the field of view. This motion was first observed by British botanist Robert Brown and is known as Brownian movement. This motion is independent of the nature of colloid but depends on the size of particles and viscosity of the solution. Smaller the size, lesser the viscosity, faster is the motion. The Brownian movement have been explained to be due to the unbalanced bombardment of particles by the molecules of the dispersion medium. The Brownian movement has a stirring effect which does not permit the particles to settle and thus is responsible for the stability of soles. Charge on colloidal particles. Colloidal particles always carry an electric charge. The nature of this charge is same on all the particles in a given colloidal solution and may be either positive or negative. The presence of equal and similar charge on colloidal particles is largely responsible in providing stability to the colloidal solution. Because of the repulsive force between charged particles having same charge prevent them from coalescing and aggregating when they come closer to one another. The charge on the sole particles is due to one or more reasons: due to electron capture by sole particles during electrodispersion of metals, due to preferential absorption of ions from solution, and or due to formulation of electrical double layer. Development of charge on sole particles by preferential absorption of ions is described below. The sole particles acquire positive or negative charge by preferential absorption of positive or negative ions when two or more ions are present in dispersion medium. Preferential adsorption of the ion common to the colloidal particle usually take place. This can be explained by taking the following examples. When highly diluted solution of silver nitrate is into diluted potassium iodide solution, the precipitated silver iodide adsorbs iodide ions from the dispersion medium and negatively charged colloidal sole particles. However, when Ki solution is added to AgNO3 solution, positively charged soles result due to adsorption of Ag positive ions from dispersion medium. If FeCl3 is added to excess hot water, a positively charged sole hydrated ferric oxide is formed due to adsorption of Fe3 positive ions. However, when ferric chloride is added to NaOH solution, a negatively charged sole is obtained with adsorption of OH negative ions. Having acquired a positive or negative charge by selective adsorption on the surface of colloidal particles, as stated above, this layer attracts counter ions from the medium, forming a second layer. The combination of two layers of opposite charges around the colloidal particle is called Helmholtz electrical double layer. According to the modern views, the first layer of ions is firmly held and is termed fixed layer, while the second layer is mobile, which is termed as diffuse layer. Since separation of charge is a seed of potential, the charges of opposite signs on the fixed and diffuse parts of the double layer results in a difference in potential between these layers. In the same manner as potential difference is developed in a capacitor, this potential difference between the fixed layer and diffuse layer of opposite charges is called electrokinetic potential or zeta potential. If two particles of an insoluble particle do not have double layers, they can come close enough and attractive van der Waals forces pull them together. When particles possess double layer, the overall effect is that particles repel each other at large distances of separation. This repulsion prevents their close approach. They remain dispersed and colloid is stabilized. The addition of more electrolyte soul suppresses the diffuse double layer and reduces zeta potential. This decreases the electrostatic repulsion between particles to a large extent and colloid precipitates. That is why colloid is particularly sensitive to oppositely charged ions electrophoresis. The existence of charged particles is confirmed by electrophoresis experiment. When electric potential is applied across two platinum electrodes dipping in a colloidal solution, the colloidal particles move towards one another or the other electrode. The movement of colloidal particles under an applied electric potential is called electrophoresis. Positively charged particles move towards cathode while negatively charged particles move towards anode. This can be demonstrated. When electrophoresis, that is movement of particles, is prevented by suitable means, it is observed that the dispersion medium begins to move in an electric field. This phenomenon is termed osmosis. Coagulation of precipitation. The stability of lyophobic sols is due to the presence of charge on colloidal particles. If somehow the charge is removed, the particles will come nearer to each other to form aggregates and settle down under the force of gravity. The process of settling in colloidal particles is called coagulation or precipitation of sols. The coagulation of lyophobic sols can be carried out in following ways. By electrophoresis, the colloidal particles move towards oppositely charged electrodes, gets discharged and precipitated. By mixing two oppositely charged sols, when mixed in almost equal proportions, neutralize their charges and get partially or completely precipitated. Mixing of hydrated ferric oxide and arsenious sulfide, being them precipitated forms. This type of coagulation is called mutual coagulation by boiling. When a sol is boiled, the adsorbed layer is disturbed due to increased collision with the molecules of dispersion medium. This reduces the charge on the particles and ultimately leads to settling down in the form of precipitate. By persistent dialysis, on prolonged dialysis, the traces of electrolyte complete present in solute are removed almost completely and colloids become unstable and ultimately coagulate. By addition of electrolytes, when excess of electrolyte is added, the colloidal particles are precipitated. The reason is that colloids interact with ions carrying charge opposite to that present on themselves. This causes neutralization, leading to their coagulation. The ions responsible for their neutralization of charge of particles is called coagulating ion. A negative ion causes precipitation of positively charged sol and vice versa. It has been observed that generally, greater valence of the flocculating ion added, the greater is its power to cause precipitation. This is known as Hardy-Schulze rule. In the coagulation of a negative sol, the flocculating power in the order is aluminum 3 positive is greater than barium 2 positive is greater than Na positive. Similarly, coagulation of a positive sol, the flocculating power is in order FeCN 6 to the power 4 negative is greater than PO4 3 negative is greater than SO4 2 negative is greater than Cl negative. The minimum concentration of electrolyte in millimoles per liter required to cause precipitation of a sol in 2 hours is called coagulating value. The smaller the quantity needed, the higher will be coagulating power of an ion. Coagulation of lyophilic sols. There are two factors which are responsible for the stability of lyophilic sols. These factors are the charge and solvation of colloidal particles. When the two factors are removed, a lyophilic sol can be coagulated. This is done by adding an electrolyte and adding a suitable solvent. When solvents such as alcohol and acetone are added to hydrophilic sols, a dehydration of dispersed phase occurs. Under this condition, a small quantity of electrolyte can bring about coagulation. Protection of colloids. Lyophilic sols are more stable than lyophilic sols. This is due to the fact that lyophilic colloids are extensively solvated. That is, colloidal particles are covered by a sheath of the liquid in which they are dispersed. Lyophilic colloids have a unique property of protecting lyophobic colloids. When a lyophilic sol is added to the lyophobic sol, The lyophilic particles form a layer around lyophobic particles and thus protect the latter from electrolytes. Lyophilic colloids used for this purpose are called protective colloids. Emulsions. These are liquid-liquid colloidal systems, that is dispersion of finely divided droplets in another liquid. If a mixture of two immiscible and partially immiscible liquid is taken, a course of dispersion in one liquid and another is obtained, which is called emulsion. Generally, one of the two liquids is water. There are two types of emulsions, oil dispersion water and water dispersion oil. In first system, the water acts as dispersion medium. Example are milk and vanishing cream. In milk, liquid fat is dispersed in water. In the second system, oil acts as dispersion medium. Common example are butter and cream. Emulsion of oil and water are unstable and sometimes they separate into two layers of standing. For stabilization of an emulsion, a third component called emulsifying agent is added. The emulsifying agent forms an interfacial film between suspended particles and the medium. The principal emulsifying agent for oil and water emulsions are protein, gums, natural and synthetic soaps, and for water in oil, heavy metal salts of fatty acids, long chain alcohols, lamp black, etc. Emulsions can be diluted with any amount of dispersion medium. On the other hand, the dispersed liquid, when mixed, forms a separate layer. The droplets in emulsion are often quite negatively charged and can be precipitated by electrolytes. They also show Brownian movement and Tyndall effect. Emulsions can be broken into constituent liquids by heating, freezing, and centrifuging. Colloids around us. Most of the substances we come across in daily life are colloids. The meals we eat, the clothes we wear, the food and furniture we use, the house we live in, the newspaper we read are largely composed of colloids. Following are interesting and noteworthy example of colloid. Blue color of sky. Dust particles along with water suspended in air scatter blue light which reaches our eyes and sky looks blue to us. Fog, mist and rain. When a large mass of air retaining dust particles is cooled down in dew point, the moisture from the air condenses on the surfaces of these particles, forming fine droplets. These droplets, being colloidal in nature, continue to float in air in the form of mist or fog. Colloids are aerosols having small droplets of water suspended in air. On account of condensation in the upper atmosphere, the colloidal droplets of water grow bigger and bigger in size till they come down in the form of rain. Sometimes rainfall occurs between two oppositely charged clouds meet. It is possible to cause artificial rain by throwing electrified sand or spraying a soil carrying opposite charge to one of the clouds from an aeroplane. Food articles, milk, butter, halwa, ice cream, fruit juices are all colloids in one form or the other. Blood, it is a colloidal solution of an albuminoid substance. The styptic action of alum and ferric chloride solution is due to coagulation of blood, forming a clot which stops further bleeding. Soils. Fertile soils are colloid in nature, in which humus acts as a protective colloid. Conductoid of colloidal nature, soils absorb moisture and nourishing materials. Formation of delta. River water is colloidal solution of clay. Seawater contains a number of electrolytes. When river water meets the seawater, the electrolytes present in seawater coagulate the colloidal solution of clay, resulting in its decomposition with the formation of delta. Application of colloids. Colloids are widely used in the industry. Electrical precipitation of smoke. Smoke is a colloidal solution of solid particles such as carbon, arsenic compound, dust in air. The smoke, before it comes out of the chimney, is led through a chamber containing plates having a charge opposite to the which carried by smoke particles. The particles, on coming in contact with these plates, lose their charge and get precipitated. The particles just settle down on the floor of chamber. The precipitator is called quadral precipitator. Purification of drinking water. The water obtained from natural resources often contains suspended impurities. Alum is added in such water to coagulate the suspended impurities and make water fit for drinking purposes. Medicines. Most of the medicines are colloidal in nature. For example, argyrol is a silver sole used as an eye lotion. Colloidal antimony is used in curing kala-azar. Colloidal gold is used as intramuscular injection. Milk of magnesia and emulsion is used for stomach disorders. Colloidal diseases. are most effective as they have large surface area and are therefore easily assimilated. Tanning. Animal hides are colloidal in nature. When a hide which has positively charged particles is soaked in tannin, which contains negatively charged colloidal particles, mutual coagulation takes place. This results in hardening of leather. This process is called tanning. Chromium salts are used for place of tannin. Cleansing action of soaps and detergents. Photographic plates and films are prepared by coating an emulsion of the light sensitive silver bromide in gelatin over glass plates or cellulose films. Rubber industry. Latex is a colloidal solution of rubber particles which are negatively charged. Rubber is obtained by coagulation of latex. Industrial products. Paints, inks, synthetic plastics, rubber, graphite, lubricant, cement, etc. are all colloidal solutions. Summary. Adsorption is a phenomenon of attracting and retaining the molecules of a substance on the surface of a solid, resulting into a higher concentration of the surface than in bulk. The substance adsorbed is known as adsorbate, and the substance on which adsorption takes place is called adsorbent. In physiosorption, adsorbate is held to the adsorbent by weak van der Waals forces, and chemisorption, adsorbate is held to the adsorbent by strong chemical bond. Almost all solid adsorb gases. The extent of adsorption of a gas on a solid depends upon nature of gas, nature of solid, surface area of solid, pressure of gas, and temperature of gas. The relationship between the extent of adsorption and pressure of gas at constant temperature is known as chemical adsorption isotherm. A catalyst is a substance in which enhances the rate of chemical reaction without itself getting used up in the reaction. The phenomena using catalyst is known as catalysis. In homogeneous catalysis, the catalyst is same phase as are the reactants, and in heterogeneous catalysis, the catalyst is in a different phase from that of the reactants. Colloidal solutions are intermediate between true molecules and suspensions. The size of colloidal particles range from 1 to 1000 nanometer. A colloidal system consists of two phases, the disperse phase and dispersion medium. Colloidal systems are classified in three ways depending upon physical states of the disperse phase, dispersion medium, and nature of interaction between disperse phase and dispersion medium. Nature of particles of disperse phase. A colloidal systems show interesting optical, mechanical, and electrical properties. The process of changing colloidal particles into insoluble precipitate by addition of some suitable electrolyte is known as coagulation. Emulsions are colloidal systems in which both disperse phase and dispersion medium are liquids. They can be of oil and water type and water and oil type. The process of making emulsion is known as emulsification. To stabilize an emulsion, the emulsifying agent or emulsifier is added. Soaps and detergents are most frequently used as emulsifiers. Colloids find several applications in industry as well as in daily life.